a new type of motion today, which is very exciting. What we have looked at so far was velocity time graphs, in particular, just made up of straight lines. So they're made up of straight lines. They might typically look like this. Velocity increasing, we have got an acceleration, constant velocity, no acceleration, and then we've got a deceleration. And so we would use gradients to find accelerations, and we have found areas to work out distance travelled or displacement. But of course, that's not very realistic at all. When you are accelerating, whether that's kind of running, whether that's in the car, on the bike, whatever, it is very, very unlikely that you are just going to have a constant acceleration. So what is more likely to happen in real life situations is that you will have some sort of curved acceleration. Might go like that, or might go like that, might be a bit kind of more wiggly depending on the terrain or depending on traffic. But certainly extended straight lines don't really happen in real life. So I've said there a few more examples, kind of cues, speeding and braking, traffic lights, and so on. And what we do, we use calculus, we use differentiation and integration. You have, for quite a long time now, been very used to finding gradients of curves by finding the gradient of the tangent, by finding dy dx. It's exactly the same here. So starting with this blue statement here, the gradients, we already know this, that the gradient of a displacement time graph gives us velocity. So if we have a curved graph like this, if we can find the gradient at a particular point t, okay, so if this is a displacement, an xt graph, if we can find that gradient, we have got the velocity. So for a curved graph, distance or displacement time graph, we know then that the speed or velocity is equal to, well, dy dx is what we would write if we had y and x appearing here. Of course, it's not y and x, it's x and t. So instead of dy dx, we are going to have dx dt. So velocity is equal to dx dt. So what we need to do, differentiating displacement, that gets us to a velocity. Okay, differentiation gets us a gradient, gets us a gradient of a tangent. And that is the definition, isn't it? The definition of velocity is how quickly distance changes. The rate of change of displacement is the definition of velocity. And we can also say the same, the gradient of a velocity time graph. So I'm essentially going to draw the same graph here, aren't I? Here is a graph. Let's do it the other way around this time. Let's have a curve there. I've got velocity on that axis. I've got time on that axis. If I want to work out the velocity at that point there, I know that the acceleration is defined by the gradient of the curve. Okay, and I didn't actually say that. Well, I said it, I haven't written it down on the previous one, have I? So the velocity is equal to the gradient. So back to here, the acceleration is equivalent to the gradient of the curve. To find the gradient of a curve, if it is v and t, we would describe that as dv dt. So in other words, differentiating the velocity, that gets us an acceleration. And then there was one more process that we did. This last process was on a velocity time graph. And on a velocity time graph, typically we had these trapezium shapes, didn't we? So we know that the area of a velocity time graph is equivalent to the distance or the displacement. So if we have a curved graph, so if we have a curved graph, let's do a bit of a straight line there, and then let's have it going a bit curved the other way. If that's a velocity time graph, again, it's the area. So it was the area here. It's the area here. Do you know how to work out areas under curves? The area, the displacement is equal to the integral. And what you normally write, you normally integrate y with respect to x. Because we've got v in place of y, we would integrate v. And instead of integrating with respect to x, we integrate with respect to t. So thinking of that, writing that in words, if we integrate the velocity, that gets us a displacement. Okay, so in summary then, wow, that pink's a bit bright. Sorry, I should change the colour. If we look at the top boxes, so let's just kind of insert a great big thing, but I need it to be inserted here. Sorry, let's move this down. So if we ignore all of that stuff, just look at this. Some people like to think of it as a process. So you've got these 3 different steps, or these 3 different quantities. You've got displacement here. I've then got velocity, and I've then got acceleration. So think, right, I've got meters per second, and I've got meters per second squared. So obviously think of them in that sequence. To go from displacement to velocity, so to go from there to there, to go from there to there, we differentiate. Similarly, to go from velocity to acceleration, we differentiate. Going the other way, if I wanted to go from acceleration to differentiation, sorry, if I wanted to go from acceleration to velocity, we would do the opposite process of differentiating. I know that going that way is differentiating, going the other way is integrating. Just said there that the velocity, if we find the area under a velocity time graph, that is a displacement. There we integrate. So going to the right, we differentiate, going to the left, that we integrate. And I actually didn't really talk about this, did I? So this here, if you start off with an acceleration, and if you were to find the area under the graph, it would be the velocity, but it doesn't tend to come up when you've got the straight line graphs as we've been doing previously. However, you will be expected to take a acceleration equation, and then integrate to get to a velocity equation. Okay, so you can either remember that as a process, or some people like to remember the equations. So by that I mean, if I can make this box smaller. So under here in red, I know that to find an acceleration, you find the gradient of velocity time graph. So it means that A is equal to v dt. Similarly, I can differentiate a displacement once to get the velocity, differentiate a displacement again, so it's actually the double derivative, d2x by dt squared. To get to the velocity, we just differentiate displacement. So that is saying in symbols there what I was saying in words here, but also these statements here. So that's velocity is equal to dx dt. Acceleration is equal to dv dt. But because v is equal to dx dt, then that is equivalent to differentiating it twice. Okay. And then on the right hand side, I think I wrote this up earlier as well. I've got them written as an equation. To find the velocity, we integrate the acceleration. To find the displacement, we integrate the velocity. So one way or the other, you need to remember these. But what it quite nicely does, it reduces these mechanics problems essentially to a pure maths problem. And I know that you all, really quite enjoyed your differentiation and your integration. The equations that you're going to be asked to do are, very straightforward. They don't tend to be, giving you all the nasty negative powers and fractional powers as you get in pure maths. These are just, look, it's a nice power of t, and it's in both of these in the questions, or in both of these terms. So this first example. A particle moves in a straight line rather, so its position can be modelled by the equation. So we don't know what it is. We don't even, need to sketch the graph particularly, although there will be some when we have a lesson next week where we will be here. We can just, work things out. We can just do the differentiation or the integration, whatever's required. So let's look at this. Part A. Find the displacement after 3 seconds. This equation, x of course is the displacement. So because x is displacement, all we have to do here, I've already been given the displacement equation. And that displacement equation, x is equal to 4t squared minus t cubed. So all we need to do is to sub in, not x is 3, t is 3. Okay, after 3 seconds, that means of course t is 3. So hence our displacement x is 4 times 3 squared minus 3 cubed. 4 9s 36 minus 27, 9 meters. Okay, and of course, I'm sure you can kind of see that if we were looking at 2 seconds, 2 seconds, does 2 seconds work? No, that would also be positive. I'm just trying to think of, there will be some values of t that you'll substitute in and you will get a negative answer. Okay, that would be nothing to worry about. That would just mean that the displacement is negative, so you're actually behind where your starting position was. Right, on to B. We need to do we need to do a bit more work here because we're asked for a velocity. Now our equation that we're given is a displacement equation. So what we need to do is we need to get from displacement to velocity. So I know that to find displacement I need to use the statement that the velocity is the rate of change of displacement, or v is equal to dx dt. Alternatively, look at the pink arrows. I have displacement. I need to go in that direction. Oh, okay, so I need to differentiate. Just think of a graph. On a distance time graph, gradient is velocity. Oh, gradient, that means I need to differentiate. So our equation is x, I'm just going to write down the x equation, x is equal to 4t squared minus t cubed. I need to differentiate, so dx dt, differentiate t squared, it's 2t, so that will be 8t, and then differentiate t cubed, it's 3t squared. So now I've got my formula for velocity. Find the velocity when t is equal to 2. I now just substitute 2 into there. So it is the equivalent really to, that is the gradient function. Now find the gradient at 2. So what we need to do here is find the velocity when t is equal to 2. So when t is 2, v is equal to 8 times 2 minus 3 times 2 squared. That is a formula that we can work out the velocity for any time at all. 16 minus 3 times by 4. So 16 minus 12, 4 meters per second, because we have got a velocity. Okay, so last up, I'm sure you've got an idea of what's coming up. Yes, we've now got to find an acceleration. So we know a velocity. We know that the gradient on a velocity time graph gives us the acceleration. So now I'm going to use the fact that acceleration is rate of change of velocity. Alternatively, kind of look at your processes, look at the pink arrows. We are on velocity, or rather we have velocity. To find acceleration, we're going in that direction and we need to differentiate. If we hadn't worked out part B, that wouldn't be an issue, because you would say, right, okay, I've got an equation for displacement. I know if I integrate it once, that would get me to velocity. If I integrate it again, that's going to get me to acceleration. So you just have to kind of go through the velocity step, even though you wouldn't necessarily need to calculate anything. So I'm going to use my velocity statement, which is here. I'll just rewrite it. V is equal to 8t minus 3t squared. So I know that the acceleration, which is dv dt, is 8 minus 6t. I know I keep writing these things down, but you know, the more you write down a is dv dt, v is dx dt, the more reinforcing that will have. Find the acceleration after 1 second. Okay, so after 1 second, that tells me the acceleration for every single time t. So I know that when t is equal to 1, the acceleration is equal to 8 minus 6 times by 1. 8 minus 6, 2 meters per second squared. Okay, so using the right formula, obviously, remembering your differentiation and your integration, which I think Mrs. James tells me that you're all wonderful at. And the people who don't like mechanics, the people who are a bit worried about it because they don't do physics, this is really quite a nice topic because it is just differentiation and some integration. Maybe example 2 might have some integration in. Now, this is a little bit odd. So you can see it hasn't liked that. Is equal to 2t minus 3t squared. Hopefully that'll work. Who knows? I think I might need a fraction there. let's change that to 3/4 t squared. Okay, all right, so find the initial velocity. So the initial velocity, this here is just code for t is equal to 0. Of course, initially, no time has passed. So it means that we need to look at substituting t equals 0 into our equation. So the initial velocity occurs when t is equal to 0. And our initial velocity, rather unexcitingly, is 2 times by 0 minus 3/4 times by 0 squared. So it's 0. That's not very much fun. The original equation could well have had a +2 or something on the end. If we'd have had a +2 on the end, then it would be slightly more exciting because our initial velocity would be equal to 2 meters per second. But let's just stick with what I've got there. The times when the body is at rest. Okay. All right, so the particle, sorry, the body, particle. By body, we obviously don't mean kind of a human body. We're meaning well, essentially a particle, just a random thing that we're not given a kind of name to, but we generally model things as a particle, so they're a point mass. Right, so when the particle is at rest, of course, it's not moving. It's not moving. It's got a 0 velocity. So the particle is at rest. That really is code for the velocity being equal to 0. So what we need to do is we need to set velocity is equal to 0 and solve that equation. Okay, so that's the 3/4 there. You could just type that into your calculator. I haven't got mine to hand, so what I'm going to do is I'm going to solve it as if it was a quadratic, take out a factor of t, and as a quadratic, it's got 2 solutions. So the first one there, t is equal to 0, which of course we knew from part 1, didn't we? We already knew that from there, initially the velocity is 0. So we knew that one of the times at which the velocity is 0 was 0. The other comes from here. So 2 minus 3/4 t is 0. 2 is equal to 3/4 t. So t is equal to 8/3 seconds. Okay, so 2 times at which the velocity is equal to 0, which we'd expect because we have got a quadratic function here. Okay, right. Find the acceleration when t is 5. So we need to find acceleration from a velocity. We know that velocity on a time, acceleration on a velocity time graph is the gradient. So acceleration is equal to gradient. So that means that acceleration is equal to dv dt. Okay, so that's how some of you might want to remember it. Of course, there you can just think of acceleration as a rate of change of velocity, or remember the diagram with the arrows. So my velocity, let's just write down the equation because it's got a bit lost beyond everything else up there. It is 2t minus 3/4 t squared. So that means that acceleration is equal to dv dt. 2 minus, so I need to multiply 3/4 by 2. So that'll be 6/4 or 3/2t. Find the acceleration when t is equal to 5. So when t is 5, the acceleration is equal to 2 minus 3/2 times by 5. So 2 minus 15/2. 2 minus 15/2, that's minus 5.5, isn't it? So minus 11/2 meters per second squared. So that means that it's decelerating. And the final part, and we haven't had to integrate yet. So is it coming now? And of course it is coming now, because what we've got to do now is to use our velocity to find a displacement. Okay, so find the displacement of the particle from A after it's been traveling for 3 seconds. So the final part. So you would think, right, the displacement is the area of a velocity time graph. So velocity is area. Oh, okay, I find area by integration. So velocity x, or sorry, displacement x or s is equal to the integral of v with respect to t. Okay, so remember that as a little equation. Remember the statement that I've written up here. Remember the graphs. Whichever way, we're going to be integrating. So we need to integrate the velocity, and the expression for the velocity is 2t minus 3/4 t squared with respect to t. When I am integrating, I increase the power, I divide by the new power. So I don't know, how do you write it? Do you use fractions, or you probably just halve it, wouldn't you? And then here I've got 3/4 t cubed. T cubed divide by 3. Okay, so that's going to make a third there. You must remember your constant. Okay, so your plus c, and you always need to remember it in your pure maths as well, but here, you know, that stands for a physical quantity. It stands for a displacement. It may be 0, quite often it isn't 0. Let's tidy that up. 1/2 times by 2 t squared. Oh, that's quite nice. That third and that 3 for a made-up example. It hasn't been awful, has it? Plus c on the end there. Just as you would do in pure maths, you'd need to work out the value of that constant. Now, this is a displacement. So I want to get some extra room. Okay, good. On to another page. So this is a displacement. So I know that x is equal to t squared minus third t cubed plus c. So we need to find c. But what we're doing here, we are measuring the velocity from a point A. Okay, so every time t, it's measuring the speed, or this equation is measuring the speed. So what this equation down here does, this x would be defined as the displacement measured from the point A. And we know that initially, so initially, t time being 0, we know that because we're measuring from A, it's got to mean that the displacement is also equal to A. So hence, if we sub those in, we can find the value of the constant. I was supposed to be subbing those in, wasn't I? So it's going to be 0 squared minus the third times by 0 cubed plus c. So C is 0. Now, that's not always the case. So quite often you might get a situation where we're starting 10 metres away from point A, or we might be starting 5 metres behind point A. So be really, really careful in the question to see, to help you to work out that constant. So that means that x is equal to t squared minus a third t cubed. And then we just had to work out, find the displacement after 3 seconds. So I just substitute 3 in there. So when time is equal to 3, the displacement is equal to 3 squared minus a third times 3 cubed. And that's equal to 9 minus 9. And again, that is quite interesting, isn't it? That is quite interesting from my just made up in panic example. What this means is that displacement is 0, hence the particle is back at its original position. So you can easily see how an exam question might say, work out the displacement, and then final part, what is the significance of your answer? So displacement is equal to 0. You might also be asked to find the distance travelled, but we should talk about that more next week. Of course, what I want you to practice today is very much basic questions where you're just